now to something completely different. Not really completely, but the centrality measures in multi-layer knowledge graphs. So I am aiming at knowledge networks and in particular knowledge graphs. And they play really a central role in modeling different kinds of information and for linking data from different domains. And thus it is widely used in big data integration, for example, in the field of biomedical information systems, this biomedical knowledge graphs, protein-protein interaction linked to document sources and so on. But on the other hand, and this is where I'm really coming from, where the examples are coming from, social network analysis, for example. The social networks are basically also knowledge graphs, knowledge networks. And the crucial point here is now that only few studies have investigated on the question how multiple layers, so these multiple layers are coming from multiple data sources or different kind of data stored in that network, how these methods impact, how these multiple layers actually impact methods and algorithms which were initially developed for single-purpose networks. So coming back to the example of social networks, initially when in the social sciences, social network analysis was developed, well, they had a network of actors, person A, person B, person C, and relations between them. But I think it came hand in hand that there was that brilliant idea to also include, for example, locations in social networks. Why not? Or companies or clubs and so on. But the crucial point here is that once we add further data, we have multiple layers. We have that location layer, we have that person or actor layer in the social network. And it is not really clear if the algorithms and centrality measures, for example, which were initially developed for single-purpose network, social network, only with persons, are still working. So what is the impact if we put more data in that? And there's a long, several decades of silence about that question. So it's widely omitted, so people simply assume that the methods initially developed still work. And what is our contribution today? Well, first of all, we have developed an experimental environment to evaluate two different centrality measures. So centrality measures are widely used in social network analysis, but anyhow, we could also expand that to other methods as well. So we have focused on degree and between centrality on random graphs, and also the random graphs are chosen from the background of social network analysis, but because it's a framework, we can also continue the evaluation on other random graphs. The outcome, the presented approach shows that the graph structures and topology, it's not a big surprise, but we have shown that it has a great impact on the robustness and of these methods. And in addition, we will make some suggestions. We have some scenarios where we have chosen particular graph structures, and we have also proven how these graph structures actually impact the outcome, the robustness. And from that on, we can think further, and we've already, I can share at the end, if we have time, I can share some thoughts which we're going to go. Okay, first of all, we will focus on the degree centrality, which is a very simple centrality measure because because the degree centrality value of the node V is actually its degree, so the number of neighbors divided or normalized by the number of nodes in the graph. And the output value ranges obviously between 0 and 1, so it's really normalized and refers to the direct connections of the. And the other centrality measure is more complex. It's the between centrality, which calculates the number EV between K and J. That is the number of all shortest paths in the network for all beginning and ending nodes K and J that pass through V. And Kj denotes the total number of paths between K and J. And the importance of V is given by the ratio of those values. You can see here on bottom in the formula. So we are actually computing all shortest paths between all pairs of nodes in the graph. And we pay special attention to all the shortest paths which pass through that particular node is. So as you can see, the first one is only a local structure, and the second one is not global structure. And we will now consider two graphs, but just to take a closer look at the impact on, thank you, the error measures. So what we basically do is we add, so we create a random graph, and I will explain that briefly because the initial idea, and we can also maybe we have a better suggestion for the experimental setup, but our idea was that we create that random graph. And then we consider part of that graph to be, let's call it blue. So that it's an arbitrary set of different information or newly added information layers. And depending on the probability called PB, for blue nodes. So depending on that probability, a larger or a smaller set of that graph will be colored in blue. And first of all, we will just remove that set and compute the outcome of the output of the algorithms or the re-centrality measures. And then we will add that and compare the output of these centrality measures without the additional nodes. So that's basically what we was from here. So first of all, we remove that blue part, and then we compute that for the complete graph, but only consider the nodes which are not. So what are we interested in? Well, okay, that I have to I will briefly talk about that because we are talking in the end about a vector containing the degree centrality or between centrality values and which are sorted decreasing. So the largest value is on the first position and the lowest value at the last. So, for example, in historical network research, they're really interested in what ancient philosopher, for example, has the highest centrality measure, and so this power. And yeah, what are we interested in? Well, first of all, we could compute the total number of misordered elements. But so let's consider this vector 1, 2, 3, 4, 5, and the second one is totally reordered 5, 3, 2, 1, 4. But let's say historian maybe sees the list and see something like that. So the fifth element is actually a position 2, and the rest is just shifted. So we have two error measures which we need to consider. The first one is the total number of misordered or reordered elements, and the second one is, do we have elements which are simply shifted in their position and have a new position? And I will. We lost. Okay. So the first error is actually the total number of misordered elements, which is noted by E. So E at the position E, C1 and C2. So it's basically 0 if they're equal and 1. And the second one is a little bit more complicated because we need to define the predecessor and the successor of an element. And for the first element, the predecessor is obviously an set, and for the last element, it's the successor is the end set. And so this is for the moved elements in the vector. Well, if both the predecessor and the successor are wrong, let's say in the new vector, then we have a value of 1, and on top, if only one of them wrong, or we have simply no errors. Both the successor and the predecessor are. Okay, and with this we can define the error errors epsilon and epsilon n, just as the sum of all these previously defined errors. And then coming back to the example with C1, C2, and C3, and we see that for between C1 and C2, both errors are actually quite high. And when we consider C1 and C3, we can see that the error for epsilon n is actually small. So this is the basic algorithm. Are we interested in just shifting, or are we interested in the complete set of wrongly reordered? And now just very briefly, coming from the background of social network analysis, we have two random graph structures which have a different distribution of node degrees. So this is the scale-free network, the so-called long tail of scale-free networks, and this is the small world networks, which has a higher number of average linked nodes, and only few low-linked and very few highly linked nodes. So two different random graphs, and we'll now come to the output. So this is the degree centrality error. Just remember that's a local structure. Degree centrality errors for scale-free random graphs. We have three different numbers of nodes, so one time for 150, 300, and 500 nodes. And on the x-axis, this is the probability for blue nodes. And actually, what you can see here is that the degree centrality is not very much affected by the probability of blue nodes. The situation changes for the small world random graph. And so the error is quite high. So this is the degree centrality. You can see here is that the epsilon n increases over time, whereas the epsilon error starts with a high value. And then this is the degree centrality error for the small world random graphs, which have more fast or higher. Okay, this is just for first orientation. As I promised in the beginning, we have considered some graph structures which have an impact on that. And first of all, we considered clique structures. So we considered one node, which is now blue, which is part of a clique in the network. And well, the situation is, let's say, more easy if we consider the degree centrality, because the degree centrality is just affected by the neighborhood of one node. And it really gets complicated when we consider degree centrality. So we have these upper bounds for epsilon, just at this point only considered affected by the position of that node in the original vector. And I will skip the group. Regarding epsilon n, it is only affected by the number of nodes which are in the graph. So we can find upper bounds for that error, which are quite. If we consider the between centrality, the things get complicated, because for these bounds we have the number of shortest paths between nodes. So we need to compute something for these bounds. They are not just given a characteristic of the graph. And the same holds for so this is for the clique structures, and we have also considered nodes which have only one other node which is connected to, so the neighborhood of that node is basically one. And again, for the degree centrality, it's quite pretty straightforward, but that's really complicated for the degree centrality. I think I should speed up a little bit. So these error estimations are not really sharp, as I said. We have to still compute the shortest path in the graph, and we don't get rid of that, especially for the between centrality. In addition, if the size of B, so the number of blue nodes, which simulate the additional data layers, increase, it will even be more challenging to specify the error rates. So remember, the initial address they were just containing one blue node. And on the other hand, we could show that blue nodes in clusters have a great influence on both epsilon and epsilon n. All those nodes with a small neighborhood have a rather small influence on epsilon n. So on the other hand, it gives us the first order of importance. Yeah, in general, we can assume, but it is not yet proven, that scale-free networks are more robust regarding epsilon n. And the degree centrality is only influenced by local structures, but in general, the errors are higher, while the degree centrality is in general more complex, and the results of this data can only be convinced. But further research needs to be done here. And we are currently working on a more generic idea, and maybe next year at the conference we can really show the results, but we are currently trying to prove a bound which is only related to the average node degree or the highest node degree and the degree of a particular node. And yeah, but maybe next year. So there is still a lot of work to do here, but according to our knowledge, we are the first to consider these artifacts which occur if we add further data to a knowledge graph or a social network, which is also a knowledge graph. And maybe you have some questions or...
Thank you very much for the presentation. I'm open discussion. Andrew? I suppose that you take into account only the classic graphs, yeah? Did you think, take into account during your research, the other type of the graphs, like hypergraphs or state graphs? It would be very interesting for the analyzing relation with the social networks, maybe more complex systems.
Yeah, thank you very much for your question and the hint. I agree, that would be very interesting, but we're at the starting point here and we will for sure consider further graphs.
Great, thank you very much for the presentation.